The final 4-mark creative question in Chapter 1 typically focuses on 2 specific tasks: calculating the total entropy of a system or determining whether a physical process is reversible. We can resolve these complex problems using a structured mathematical framework. By following this sequence, you can consistently arrive at the correct net entropy change. Prepare your scientific calculator, a pen and paper to map out this process. This framework converts a multi-layered word problem into a sequence of predictable calculations. To begin the calculation, you must translate the descriptive language of the problem into thermodynamic variables. The specific adverbs used in the text dictate which formula you need to apply. If a gas expands slowly, it signifies an isothermal process where temperature remains constant. Conversely, if a change happens suddenly, there's no time to exchange heat. This is an adiabatic process where delta Q is 0. Identifying these technical indicators in the text is the necessary first step before writing your equations. The choice of formula depends entirely on these descriptions. Misidentifying a single adverb will result in an incorrect calculation for the entire system. For entropy, choose a path based on changing temperature or phase. For temperature changes, use the left path formula with specific heat and the natural log temperature ratio. For phase changes, use the right path with latent heat. Crucially, convert every temperature to absolute Kelvin. If the problem provides a value of 27 degrees Celsius, you must add 273. The resulting 300 Kelvin is the value required for the equation. Selecting the correct path and applying the Kelvin conversion ensures accurate baseline entropy values. For gas-specific entropy, we apply the volume expansion formula. For 1 mole of gas expanding from 50 to 100 units, using the gas constant of 8.314, we set up the natural log ratio. On your calculator, enter the sequence exactly as shown. 1 times 8.314 times the natural log of the volume ratio, 100 over 50. The final value is 5.76. Because the gas volume increased, the entropy change is a positive 5.76 joules per Kelvin. If the problem describes an adiabatic process, the calculation is significantly shorter. By definition, adiabatic changes involve no heat transfer. Since delta Q is 0, the resulting entropy change, delta S, is also 0. Identifying adiabatic processes allows you to quickly assign a value of 0 to that step, preserving time for the rest of the exam. To aggregate your findings, sum the individual entropy changes for every process. The result determines the system's nature. If the total net change is exactly 0, the process is reversible. If the total change is greater than 0, the process is irreversible. Providing this final sum and the corresponding diagnosis of the system satisfies all requirements for the 4-mark question. You now have a complete framework for translating descriptive text into precise thermodynamic calculations. Refer to this summary for your final review. These 4 formulas and the Kelvin conversion rule cover the majority of entropy variations found in the HSC syllabus. Apply this framework to the practice question provided in the pinned comment. Approaching these creative questions with a systematic mathematical logic allows you to navigate the exam with clarity and precision.